Okay, we will start now with exercise number 2. Look the difference between this exercise and the one before. First, we used to have one force or two forces that were punctual like this. It's like a point, a force that is in a point. Now we have something different. We have a distributed force. Think about this distributed force like a series of arrows that are acting in a surface that has a length of 4 units, from 4 to 8. And this force is a force of 10 kilonewtons per meter. It will be the same for effects of this exercise if it is 10 pounds per feet. Well, that means that every feet, 1, 2, 3, and 4, for each one of them, we have 10 pounds. 10 multiplied by 4 is 40. Well, the total force of 10 kilonewtons could be substituted by 40 kilonewtons, not by meter, but 40 kilonewtons, or 10 pounds per feet can be substituted by 40 pounds. Well, it's very important to understand what is the denomination of this force. If it is divided by the units of length, that means that the total weight need to be multiplied. The total weight will be, all this weight will be 40. Instead, if here is written 10 kilonewtons, so 10 pounds, you don't need to multiply. That is the weight of the total element. Well, what we will do, when we have this type of distributed force, the curves and the inclined lines in both diagrams will be different in shear and moment. But for the effects of calculations, it's not necessary to think that we have a distributed force. We can change this distributed force that we have in this place. Let me go back, sorry. This distributed force that we have here of 10 kilonewtons per meter, that is total 40, we can substitute for an identical force in the middle with the total value that is 40. And that is what we did here. Here in the middle, in 6, we have a force of 40. In order to calculate the reaction, this diagram is exactly the same as this diagram. Well, we will transform those two diagrams that are the same. We will transform in this diagram. We will substitute for a force in the middle. And the results of the reactions will be the same for both. The reason why we change is that it's much easier to calculate this one, because here we will need to multiply many arrows. There are infinite arrows there, and that will take a lot of time. Therefore, we substitute. After we substitute, that is something important, we will forget this one. After we calculate the reactions, we will forget this one, and we will go back to the original in order to make the two moments and shear diagrams. But as I explained, today we will not be working with moment and shear diagram. I have this information for the next time. We will work only with the reactions. Well, my recommendation is the following. For an exercise very simple like this, it will be easier to just write an X there, right here 40, because 10 multiplied by 4 is 40, and right here the number 6, and then you can do all the calculations. But you can get confused. Some students get confused. They forgot that if you do that, it's like this element doesn't exist anymore. And sometimes the exercise is very complex, and those numbers here will be tricky. Well, I don't recommend you to do this. I recommend you to draw again. Here, draw again the diagram with the new values, and then you do your calculations. And after you finish, you take these values, 20 and 20, you put them here, and you can continue with the information. As you know, this is the information that we receive. After this information, that is the same of this diagram, we'll write these two numbers. And finally, we can able to calculate the two diagrams. Well, let's look how we calculate the sheet. Is very easy after we do the reaction, sorry. It's very easy after we make this substitution. Things are very simple. We will do like in the first exercise. You have reaction 1 here, reaction 2 here, and you tell summatory of moments in R1, I am at this point, is equal to R1 multiplied by 0, this is 0. We are speaking about this force. The distance that separates this force to the place where I am is 0. I start moving around, and I find a first force, 40. This 40 is pushing down, I will call this minus 40 multiplied by 6. And that will be 240. I continue going there, and I find another force that is R2. You will multiply R2 by the distance that separates R2 to the place where you are. Is 12. Is not 14. We have 14 here. This being is longer. We have here a little piece, but this piece, because there is no any force over there, we will not use for the moment. We are not using this part. If we had here a reaction, then we need to use it. But for the moment, we don't do it. Well, we do exactly the same. We take out R2 from this equation, and the result is 20. After we finish, let's clear, and we put an X in R2. This is our reaction. And we start calculating how much is the summatory of moments in R2. The summatory of moments is every force multiplied by the distance of the place where I am. And I like to put an X there to don't forget that we are there. Well, R2 multiplied by 0, because we're in the same place, R2 disappear. That is wonderful, because now we can calculate R1. This is R1 here, I apologize. Let's go. First, 40 multiplied by 6. This is the distance from 6 to 12. Second, R1 multiplied by 12. This is the distance, 12. We take R1 from the equation. This is 240. Go to the other side, positive. 12 multiply, go dividing, and R1 is 20. By coincidence, R2 and R1 are the same number. And it's correct, because 20 plus 20, reaction 1 plus reaction 2 is equal to 40. And remember, this 40 came because this is 10 kilonewtons, 10 multiplied by 4. We need to put the total weight when we do the substitution. And with that, this exercise is ready. We can start the next time to do the shear and bending diagrams. Let's go now to the next exercise, exercise 3. Here we have a combination. Look, we have a force. Let me go back, I'm sorry. We have a force that is 20. That is, this is tricky. Let me go back again. I'm running fast. We have a force that is 20. In the stream, near the stream, we have a distributed force of 10. That is what we receive as an exercise. I will put that information there in order to do all the drawings. And this is what we will make the substitution. And what we do is simple. We put here this force that is 10, look, 10 multiplied by 4 is 40. We put 40 there in the 0.6 like before. Well, we substitute, this element is eliminated, and the only force that we have is 40 in this point. Let's calculate the reaction in 1. And reaction 1 will be R1 multiplied by 0 disappear, okay? 20 multiplied by 2, negative because it's pushing down 40 multiplied by 6. This is this distance, 6. And finally, 12 multiplied by R2. That is the R2 that is there. We take out R2 from the reaction, and it's 320 divided by 12. R2 is 23.33. That's it. We can do the same for the vertical forces. We calculate, we substitute again, as I explained you here, we will locate 40, and we calculate in R2 our moment. R2 multiplied by 0 disappear, okay? We go here, 40 multiplied by the distance, 20 multiplied by the distance, R1 multiplied by the distance, and we have 32.66. If we don't want to do that, we can just, and I recommend you to do it, you can just be lazy and just tell yourself, because I know that this is 23, okay? R2 is 23 here, well, 23.33, well, the other one is 40 plus 20, 60, 60 minus 23, that is R2. And you get it. You have two possibilities, but I recommend you to do again the summatory of moments, and after you do it, you corroborate with the last one. Let's go with the exercise 4. The exercise 4 is a little bit more complicated. We have only two forces, but look what happens. In the past, we have things like this. We have the forces between, always between the places where we are doing the calculation. If we calculate here, all the loads were at the left. If we calculate here, all the loads were at the right. But this case is different. When we calculate the moment in R1 in this point, that is the center, this point, this force will be negative, 20 will be negative, and 10 will be negative. Why? Because they are in the same side, in the right side. Okay? But when we calculate the reaction here in R2, we have one force at the left and one force at the right. And that is something similar to this. Imagine that you have a person, here you have, I will make this bigger. You have a person with the two hands, and this person is carrying a load brown here, and another load that is yellow here. Let's make it really yellow. What happens when we want to calculate the moment in the center of this body? This force will push these hands to this direction. It will push them down to this direction. This is clockwise, but this hand will be pushed in this direction, will be pushed down like this. And this movement here is clockwise. This is counterclockwise, sorry, contrary to the clock. They are different, they cannot have the same sign. Well, here happens the same. If I calculate the moment in R1, 200 can be negative, and 10 should be negative, and 18 or whatever is reaction 2 will be positive. Or I can tell the contrary. This is positive, and this is negative. The important is that all the forces here will have the same sign, and all the forces there, that usually is only one, will have the same sign. But if we do the calculation there, we cannot do that because of this explanation. If this force is negative, this is positive. If this one is positive, this one will be negative. Well, after you understand that, you can just decide it. You can tell yourself, well, this sign that is clockwise is negative, for example, and you put the sign here, and you see it's contradictory to your sign. That means this is positive. You move your sign and you put the sign there. And now it's working. Look, it's working with 20. That means that it's also negative. And you can do the same going there. And you can do the same going here. But there you will get confused because it's the same side. Well, that's why I don't like this idea of this little paper method to be moving the stuff. I think that it's easier that you just tell yourself, if I am at the left, everything that go is negative, everything that go there is negative, everything that go up is positive. Again, if I am in the right, this guy is negative because go down, this is negative because go down, this is positive because go up, this is positive because go up. However, when you are doing the calculation in the middle, in an area that is between two forces, these need to be different. Well, if you put this positive, this is negative. This is no matter what is the sign, because it's in the same place, will be multiplied by 0 because this is negative, this that go up is positive. And that's it. Let's do it. Summatory of forces in R1. Let me try to clean here again. I will put my X here and I say summatory of moments in R1 that is here is equal to, I start moving and I find 20. Well, first R1 multiplied by 0 is 0. I find 20. I decided that 20 is negative. 20 multiplied by 4, that is this distance. Continuous walking, nothing happens. And I find 2. One reaction, that is R2 multiplied by 12. This is the distance. And after minus 10, that is this one, sorry, I did a mistake, minus 10, go at 10. Minus 10 multiplied by 14. That is this distance. Well, look that both are negative. Why? Because both are at the right. With volt operation, and this is the value of reaction 2. But now we have a difference. Now we will calculate the moment in R2. That means they need to have a different sign. Summatory of moments in R2 is equal. R2 multiplied by 0, disappear. I go first to the left. It's no matter if you go first to the left or to the right. I will tell that this is negative, therefore this is positive. Minus 10 multiplied by 2, because this distance is 2. Second, I go to the next one. 20 multiplied by 8, because this distance 12 minus 4 is 8. And finally, R1 multiplied by 12. Attention, don't multiply R1 by 14. Yes, 14 is this distance, but you are not in the end of the beam. You are calculating in this point. This is the distance that you need. And you do everything together and you arrive to 11.666. Finally, let's go to the last one. The last one will be calculated by you guys. And I will explain you what you will be doing. You need to complete the diagram and substitute 20 kilonewtons per meter and 50 kilonewtons oh, I'm sorry, let me go back. 50 kilonewtons sorry, you will substitute 50 kilonewtons that is here, okay, by 40 in the center and 350 in the center of the distributed force. I mean, these kilonewtons, 20, is in a distance of 2. That means 20 multiplied by 2, the value of this force is 40. And you will put 40 in this point, in the center. After the value of this force, let me change color. Let's take the yellow. Let's take something stronger. The pink. The value of this distributed force that you imagine that are like many books, it will appear like many elements like this, is 50 per meter. And how many meters we have? we have 7. 50 multiplied by 7 is 350, Well, you will put 40 in this place, in 5. You need to put 40 here. And after, you need to put 350 here in the center, okay? And the center of this one will be 12 minus 5, that is 7. And you will put in the middle of 7, that is 3.5. 1, 2, 3.5. In 8.5, you will put that force. About here, 8.5. And that force is 350. How you will do this? Have the solution already. And the equation that you will be using will be, you calculate the moment here, and it's 20 multiplied by 4, 40 multiplied by 6, 350 multiplied by whatever number is that, I guess 8.5, R2 multiplied by 12, 10 multiplied by 14. 10 is negative, 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 and this is positive. For example, if you change all the signs and all the ones going down like this are positive, then R2 is negative. The result is the same. After you do that, let's clean everything. You will do the same here. You will tell this is R2, therefore 10 multiplied by this distance, let's tell that 10 is negative. 20 multiplied by this distance, now 20 is positive, and in 8.5 you put 350, and here in 7, 4, I think that was here, in 7, 4, 5, 6, 7, sorry, I told that wrong before. In 7 you will put 20, etc., etc. And you will calculate the two values, calculating the summatory of moments in R1, you will calculate the summatory of moments in R2, you will get these two values, and when you put them together, they need to be equal to 350 plus 40, that is 390. Okay, and that concludes this presentation. You have many exercises in the book. We'll try to do the exercises of the book, and you have some more exercises that are after this one. We'll try to make all of them to be sure that you understand these diagrams. You will have 2 diagrams like these ones. Sorry, not 2 diagrams, 2 beams like these ones, and you will need to calculate the reaction 1, reaction 2. Thank you very much.